After watching this video lecture, students are going to be able to define salts and their behavior in solution. You're going to be able to discuss the salt's effect on the pH of solutions and calculate pH of salt solutions. So what is a salt? Basically, a salt, guys, is just another name for an ionic compound. Basically, you're going to have a cation, which is a positively charged ion, combined with an anion, which is a negatively charged ion, to form a compound. Now, when we place a salt into water, we know that it breaks up into the ions that comprise it. So basically, you're going to have a positively charged and a negatively charged species. Now, depending on what the source of the anion and cation would be with respect to an acid or a base, that's going to dictate its behavior in the water. Okay, so we're going to go ahead and look at that in great detail. So for some salts, the ions that get placed into the water when they dissolve cause pH changes because the ions themselves can behave as either acids or bases. Okay, so if we look at the example NaF, okay, it's going to break into Na plus and F minus. So in that particular case, what we end up having is F minus here capable of behaving as a base. Okay, and we'll talk about how that, or why that process occurs here in a minute, but the interaction of F minus with water is known as hydrolysis. So what's going to happen is F minus is going to behave as a base, and H2O is going to behave as an acid, and so what we're going to end up with is the following conjugate acid and conjugate base. Okay, so in this context, this base, which is being sourced from this salt when we place it in water, is basically behaving as a weak base in solution and producing conjugates, as we see here. Now, the pH of these salt solutions can be calculated, and we'll look at the detailed process that here in a little bit. Okay, and basically the pH of the solution is going to be dictated by the characteristics associated with the cations and anions that we find in the salt. So let's go ahead and let's discuss how to determine whether the cation and anion that's being produced in a solution containing a salt will behave as an acid or a base. So guys, an ion's ability to react with water is going to be dictated by the strength of the source, acid or base, that ion would be generated from. So if we go ahead and we look at the first characteristic, the ion, if it's sourced from a strong acid or strong base, it's going to have negligible effect on pH. Okay, so what do I mean by being sourced from a strong acid or strong base? So if we go ahead and we look at the chloride ion, okay, so the chloride ion we know would be a conjugate base of HCl, because if we look at the dissociation process of HCl, we get H plus and Cl minus. Okay, this is our conjugate acid, this is our conjugate base. So chloride in this case would be the conjugate base of the strong acid HCl. Okay, so now listen guys, remember that the equilibrium lies very far to the right for strong acids and bases. Okay, so because of that, this chloride ion doesn't want to reverse the process and produce HCl. So when I put Cl minus into water, it doesn't want to form the HCl and hydroxide ion. Okay, this is not something that's going to be favorable. So that is why when we place a salt like sodium chloride into water and it gives us Na plus and Cl minus, that's why we don't see a pH change associated with the chloride ion. Okay, now conversely, if we're looking at sodium chloride as the example here, once again, Na plus ion, the sodium ion, is an ion that we could necessarily need to look at. So the source here would be NaOH, okay, and sodium hydroxide is a strong base. So the sourcing from a strong base is going to mean that the sodium ion also does not affect the pH of the solution. So if we add a salt that contains ions that are sourced from strong acids and strong bases, we're not going to see a pH change. Now conversely guys, if the ions are sourced from a weak acid or weak base, that's going to cause pH changes. Okay, so if we have something like F minus, okay, or the fluoride ion, okay, if we look at its source, okay, so HF would be its source, acid. Okay, and we would get the following conjugate acid and base from the dissociation process associated with HF. So this is my conjugate acid, this is my conjugate base. So in this context, guys, we know that our equilibrium here actually lies far to the left. So in that context, when I put a salt, such as sodium fluoride, in solution, and basically allow that fluoride ion to interact with water, what I end up with is the reversing of this equilibrium position for the regeneration of HF. Okay, so in the context here, F minus, because it's sourced from a weak acid, is going to behave as a weak base in solution. Okay, so the same idea can be applied to something like NH4 plus. Okay, so NH4 plus is a conjugate acid of a weak base. Okay, so if we look at NH3, place that in water, okay, that's going to form NH4 plus ion, okay, as well as hydroxide ion. So we've placed those in water, and what we notice here is that we produce this conjugate acid, and of course this conjugate base. Now, the NH4 plus, we know that this equilibrium position is going to lie far to the left. So when we just put a salt that contains NH4 plus, such as, I don't know, ammonium chloride, this NH4 plus is going to behave as an acid in solution. So in this context, we'll also see a change in pH. Okay, now, obviously, guys, if we have something that's behaving as an acid in solution, that's going to decrease our pH. And if we have something that is behaving as a base in solution, that's going to increase our pH. Okay, so those are things to remember and think about. Okay, now some of you may be asking, well, what if you have something that has an ionizable proton? Okay, when we've seen this with our polyprotic acids. In that case, you're going to have to look at Ka and Kb values. If the Ka value is greater than the Kb, then the solution will be acidic. If the Kb is greater than the Ka, the solution will be basic. And if Ka is equal to Kb, then the solution will be neutral. Okay, so now let's go ahead and let's talk about some other examples of cations that can affect the pH of our solutions. Okay, so there are cations that also have the ability to react with water in a somewhat unique way. So in the case of metal ions that are very small and have very high charges, as we see with the examples here, what ends up happening is when we place them in water, the water molecules aggregate to the cation. And what ends up happening is that positive charge pulls electron density away from the OH bonds that are in the water molecules. And so what ends up happening is it makes it so that the proton here is more easily ionizable and basically allows water molecules to come and snatch away those protons and produce hydronium ions. So what's going to happen in the case of examples where you dissolve small highly positively charged cations into solution, you're going to end up increasing your hydronium ion concentration or increasing your H plus concentration. And with an increase in H plus concentration, that's going to decrease the pH of your solution. Okay, and basically, you guys may want to familiarize yourself with this process here because there obviously could be questions regarding what's happening to the pH and why, and you guys want to be able to think that through. So we're going to calculate the pH of a salt solution of KSCN by utilizing the conjugate base acid relationship between HCN and the common ion found in the salt. Okay, so KSCN, guys, when we place it into water, okay, it's going to break into K plus and Cn minus ions, okay, because that's how salts behave in solution. Now, if we go ahead and we look at the ions that are produced, K plus would be sourced from the strong base KOH, so we know that its presence isn't going to change the pH of the solution. However, Cn minus would be sourced from HCN. Okay, and HCN is a weak acid, so what that means is it means that this ion here is going to behave as a base in solution. So Cn minus, when placed in water, is going to produce HCN and OH minus. Okay, so that Cn minus is behaving as a base and producing hydroxide ions in solution. So we're going to go ahead and we're going to calculate the pH of a solution containing this base Cn-. Okay, now this is going to require just simple setup ice tables. And of course, we're going to be doing an equilibrium expression. Now, in this context, what I want you guys to notice is that the equilibrium constant or expression for this process that we see here is going to be related to a base. Why? Because Cn- is behaving as a base. So we're going to have HCN, OH-, okay, and then the concentration of Cn-. Now notice I've excluded H2O because once again that's a pure liquid. Okay, now you may be asking or maybe saying, well, we don't have Kb. Okay, the reality of it is we do not have Kb. However, we have the Ka of the acid that contains a common ion, Cn-. So we can utilize Ka times Kb equaling Kw to help us out with this process. Okay, so let's go ahead and quickly solve for our Kb. So Kb is going to be equal to Kw over Ka. Okay, so Kb is equal to 1 times 10 to the negative 14th divided by 5.8 times 10 to the negative 10th. And if we plug this into our calculator, so that is going to be 1.72 times 10 to the negative 5th as our Kb value. Okay, so now that we have our Kb value, let's go ahead and plug in what we know for our ice table. So 0.500 is the concentration of our Cn-, because there's a one-to-one relationship between Kcn and Cn- for the dissociation. Okay, and we're going to put 0 and 0 here. Notice, guys, I'm ignoring H2O through this process because it's not part of the equilibrium expression. Okay, so minus x plus x plus x, 0.50 minus, 0 minus x, x and x. Okay, so Kb is going to be equal to x squared over 0.500 minus x, which is going to be equal to 1.72 times 10 to the negative 5th. Okay, we're going to assume that x is small. And because we're assuming that x is small, that's going to give us x squared over 0.500 equaling 1.7 times 10 to the negative 5th. If we go ahead and solve for x is going to equal 2.9 times 10 to the negative 3rd. Okay, now guys, our x value corresponds to our concentration of our hydroxide in solution. Okay, so if we know the concentration of our hydroxide ion in solution, we can calculate pOH. And pOH is going to be equal to the negative log of the concentration of our OH minus. Okay, so if we go ahead and plug that in, pOH is going to equal 2.54. Okay, and they want pH, so we're going to have to use this equation to get our pH. And so 14 minus 2.54, pH is going to be equal to 11.46. Okay, guys, this is just how we approach these problems. One more thing I do want to mention, guys, is that you do want to make sure that your assumptions with the dropping of x is acceptable, just in the typical way we have in the past. So remember, we need to be under 5%. But other than that, these problems are pretty straightforward, the hardest part being identifying what species are actually going to cause changes in pH. Okay, so let's go ahead and look at the problem here. Again, we're looking at a salt being dissolved in water, and they want to know the pH associated with that. So NH4 Cl, when we dissolve it in water, is going to give us NH4 plus and Cl minus ions. Okay, again, Cl minus doesn't affect pH because it would be sourced from strong acid HCl. NH4 plus, on the other hand, is going to be sourced from the weak acid NH3. Okay, so NH4 is the ion that we actually care about in terms of how it behaves with water. Okay, so in this case, NH4 plus is going to behave as an acid. So that acid is going to give us H3O plus and NH3. Okay, and so if we go ahead and write our Ka expression, notice this is behaving as an acid, and so the ionization process that we see here is associated with an acid. That's going to be H3O plus, it's going to be NH3, okay, and then we're going to have NH4 plus. All right, now obviously Ka is what we've been going to be calculating for this process. However, we don't have Ka, we have Kb for the conjugate base. So again, we're going to utilize the Ka times Kb equals Kw. Okay, so our Ka is going to be equal to 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5. Okay, if we plug that in our calculator, so Ka for this process is going to be 5.55 times 10 to the negative 10th. Okay, and that's going to be equal to the H3O plus concentration, the NH3 concentration, and the NH4 plus concentration relationship that we see here at equilibrium. Okay, so now we need to actually get these values, and we're going to get them from our ICE table. Okay, so initial value, they've told us that we have 0.10 moles of that. Again, we're avoiding H2O or ignoring H2O because it's not part of the equilibrium expression. Our changes will occur as follows. Okay, and these are equilibrium values. So if we plug these into our equilibrium expression here, we get x squared over 0.10 minus x being equal to 5.55 times 10 to the negative 10th. Okay, and once again, I'm going to assume that x is relatively small. Okay, so we're going to go ahead and cancel out x. And so our x squared is going to be equal to 5.55 times 10 to the negative 11th. And if we take the square root of that, we get our x value being equal to 7.5 times 10 to the negative 6th. Okay, and so x here corresponds to the concentration of H3O plus. So if I know the concentration of H3O plus, I can easily calculate my pH by taking the negative log of that value, which is going to give me 5.13 as my pH for this solution. So basically, guys, it's a similar approach to what we saw in our last problem, and you just kind of take it and analyze it from the perspective that we did with the last example. Okay, so guys, some of you may be wondering about situations where salts are placed in water that contain conjugates of weak acids and weak bases. So an example of that would be like what we see here. Okay, so the ammonium acetate here. The question is this going to be acidic, basic, or neutral when we put it into water? You know, is the ammonium ion or the acetate ion going to affect the pH more? Okay, and so the way we're going to look at these is we need to compare our Ka's and our Kb's for the species present. Okay, so if the Ka is greater, it's going to be acidic. If the Kb is greater, then it's going to be basic. If they're equal, it'll be neutral. All right, so if we go ahead and we look at the Ka for ammonium and we look up the Kb for the acetate ion, we see that we end up with a Ka and Kb that are equal to one another. So in this particular case, when we dissolve ammonium acetate into water, it's going to be a neutral solution. So again, looking up data or possibly being provided with a table or appendice that allows you to assess Kas and Kbs, that of course will be given to you so that you can make this assessment in these types of problems.